The Department of Defense owns a lot of flammable forest land around their installations, and they have a vested interest in understanding how to best manage fire in those fire-prone forests. So I'd like to start my presentation today talking a little bit about models, and Nick got into this last week, but even as an ecologist, the term models sometimes used to throw me off a little bit before I knew as much as I do about them now. So what does a model do? A model can be, I think, of paper airplanes or model airplanes. And so we have a picture of a paper model airplane of a Boeing 77 and an actual Boeing 77 here, 777. And you can learn things about a model that doesn't have to be exactly perfect like the real thing. So we can learn a little bit about the structure of an airplane, about what the inside of it looks like by looking at a model without having to have a multi-million-dollar thing taking up a lot of space in the backyard. We could also take a scaled-down model of an airplane, in this case, and we could put it in a wind tunnel. We can learn about the physics of how the larger thing would interact with its environment. And this is how airplane engineers actually design better wings and better airplanes to accomplish the goals of airplanes, maybe carrying a spacecraft or flying real fast to get somewhere. We can also take that information about something we're interested in, like an airplane, and we can create a numerical model. Instead of having to build an actual physical thing that we can hold, we can numerically represent every part of that that we know about in a computer program or in a script, and simulate how that should behave in different environments. And then, again, that saves time, and it allows us to do different types of experiments quickly or cost-effectively, or without the need of taking time to build complicated things. So this same principle is how wildland fire dynamic simulators work. We have, you could build, or we do have numerical models of the forest, how the fuels are structured for different types of places, and they're integrated into these different simulation tools, which you may or may not have heard of. So all these tools are based really in Rothermel's fire spread model. This was the origin of these tools, and Nick talked about this a little bit previously. And the way these models work is they have numerical representations of things like wind and slope, and there's constants of fire combustion properties. And then there's a fuel model. So that's a model within a model, a representation of fuel within another representation of how fire moves. And that all goes into calculating fire spread and fire intensity. So fuel models. There's lots of different fuel models available, but not so many that we can really characterize every different condition very well. And that's kind of the crux of where we're at right now scientifically, and part of the focus of this study. Rothermel came up with 11 different models of what fuels are like across the country in 1972. Then Albini and Anderson characterized in two separate papers an additional 2 models. And then Scott and Bergen gave us a total of 40 models, and they can be classified into different environments like grass or timber. But these are sort of simplifications of what the natural environment is like. So this is just a land fire produced map of the 13 fuel models that Anderson presented, and some of these are still commonly used. And then there's the Scott and Bergen 40. And if we look up in the Northeast, it's a little hard to see, but so here we are. That doesn't make it any better. Right. So if we look in the Northeast, we can see there's not a whole lot of different fuel conditions represented in these models. But there's actually a lot more different conditions out there that we've seen if we've been on fires. And so this is how this information gets integrated into a modeling tool. We've got measurements of slope, aspect, canopy cover, height, and fuel. And they're integrated on a spatial cellular scale, and then they're run across an environment. But there's a lot of assumptions about these models. An important one is that within a cell in the model, there's no real variation in bulk density, fuel loading, or depth. Structure, so that might be your ladder fuels, or just the structure that of plants that influences flow in the forest. That's homogeneous. Moisture content among the different things growing there is homogeneous. And then we're making assumptions about spatial scale too, that a lot of these data are available or measured at the stand level. And so that's essentially the level of a burn unit. And we know that there's a lot more variability across an individual burn unit. Also, things like heat of combustion, heat release, which are going to get covered in a couple presentations ahead of today by some of the engineers we work with, but also time of year and how that influences fuel characteristics. So all these things are really important in prescribed burning. Just go back here. Yeah, so all these things are really important in prescribed burning because we're taking advantage of these nuances of fuel and season and structure to accomplish goals in prescribed burning that are more nuanced typically than wildfire management. And so prescribed burning fire managers will use subtle changes in topography to find different balances of moisture, or they'll burn when vegetation is a particular way because it provides the right level of flow to get wind through the forest and carry the fire well. This is a LiDAR map actually after a series of prescribed burns that were conducted in Penn State Forest in the New Jersey Pine Barrens. And if you're using some of the publicly available tools that might work okay out west in a very large area, this would only take up a couple pixels. These pixels are, I'm not exactly sure, but they're probably about 8 to 10 feet in size. And so we can see there's where there's blue in the picture here, that's low fuel loading, and where there's red, there's high fuel loading. And we can see that there's lots of change. Some places are very similar. Some places change very quickly, across a short distance. And these characteristics all come into play with fire behavior for future prescribed burning or in a wildfire situation. So here's just a picture of prescribed burning at the Albany Pine Bush Preserve, and we can see we're violating a number of assumptions right here that might be used in some of these traditional modeling tools where we've got multiple ignitions going on, using multiple spot ignitions to control fire behavior. These fuels have been burned and mowed previously to achieve a unique balance of wet and dry material that will combust in a desirable way. And then we've also got a lot of differences in structure across this picture here. So in the bottom left, you can see there's not a whole lot of structure, not a whole lot of material there. But as we move to the forest, there's more shrubs, and then we've got trees here. And here is just another picture from that same day, and you can see the effect that there's hardly any smoke being put off by this fire because the timing of this fire with the fuels and so the live and dead fuels is producing a very hot fire that's consuming quite a bit and has a very complete combustion. So that's desirable for smoke management and for achieving the ecological goals of that fire. This is a dormant season fire, and you can see there's also a lower fire intensity occurring in this picture, and there's actually a lot more smoke being produced because it was a bit colder and a bit wetter. This is just another picture of a fire down in Florida where Unfortunately, the conditions of the fuel ended up being the live fuel was wetter than we wanted, and we just weren't quite able to achieve the level of fire behavior we wanted to actually thin out the forest more. So just a couple different ways that these nuanced things about fuel really come into play with prescribed burning. So whether you're prescribed burning for forest regeneration or for endangered wildflowers, there's the pine barrens gentian there, habitat for Carner's blue butterfly, or habitat for quail or timber, the nuances of fuels are very important, and whether it's always acknowledged, they're actively taken advantage of by fire managers. So this is pretty interesting. This heterogeneity of fuel characteristics that isn't always looked at actually presents us with a lot of interesting questions for the next generation of fire modeling tools. So, for instance, looking at how bulk density and fuel in terms of and loading and depth actually vary across space and how that impacts fire behavior. Looking at how structure impacts flow of air through fuels, and how that changes with different types of fuels, the different species mixes of plants. We can look at how moisture content varies across live and dead fuels, both seasonally and just across a given day. And then we can look at things like spatial scale and how important, what points the spatial scale change. On a large wildfire, if you've got a couple more kilograms of 10-hour fuels, but you've got 100-foot flames already out the top of the canopy, those extra couple kilograms of 10-hour fuels are probably irrelevant. But in a low-intensity prescribed fire, the subtle changes in fuel loading and conditions really can impact your outcomes. So how do these things vary is a really interesting question, and there's that we're trying to inform. So, and all that information will go back into a new wave or a new generation rather of fire behavior models that are associated with the WFDS model, and so that's in its development stage. I thought I had a slide on it, but I don't see it. So again, there's all these different kinds of heterogeneity, and they're going to get incorporated better with physical relationships into this new modeling tool. Here we go, WFDS. So right now, we're in the field data collection, if we look in the upper right here, and that will feed back into modeling and simulations, and that will be supported by laboratory measurements, which you'll learn about a couple webinars down the road here by our colleagues in some Worcester Polytechnical Institute and University of Edinburgh. And then that will feed back into more field data collection to fill in gaps. So we're kind of short on results at this point because we're just coming off of our first major field season for this project. But there are a couple interesting preliminary results that I have to share with you today. And one of them, so we're going to get all this fuels data, and how do we make sense of it? So one idea is to make a fuels library that can be incorporated into numerical simulations. So if, just like a plane, we can scan and get digital representations of fuels, different types of fuels, and their structure. So this is just a two-dimensional picture of blueberry stems of different ages, or actually different times since fire. And so, as you can see here, the structure of a blueberry plant changes dramatically over from year 1 to year 20 with time since burning. And so the overall length of material, the number of branches or levels of branching change dramatically. And this can get incorporated into model simulations where we can say, well, what is a shrub layer that's 2 years post-prescribed fire going to burn like versus one that's 20 years post-prescribed fire? And we can analyze how flow in these different environments will vary. Another thing that we've already looked at a little bit is live fuel moisture, and so that varies quite a bit seasonally in pine. This is 2 different sites that we looked at in the Pine Barrens, and you can see that around week 20, which is just about the end of April, early May, that we hit the annual low point for fuel moisture, whereas in around week 30, we're up at about 160%, or almost, the pine foliage has almost twice the moisture in it at that point of year. And these differences actually correspond with historic prevalence of wildfires and the severity of wildfires, such that around week 20 happens to be kind of the hot spot over the past 100 years for severe fires. And then that sort of tapers off as coincidentally, or maybe not coincidentally, as fuel moisture increases. So we've started looking at fuel moisture of some shrub species as well, which hasn't really been characterized. So this is, again, just some preliminary data. We haven't gotten very far into the year. But if you look, the blue bars indicate measurements from January 5th, and the first green bar indicates a measurement from April 1st, and the third one indicates a measurement from April 23rd. And if we look at Quercus ilicifolia here, we can see that in January, the fuel moisture was somewhere around in the mid-30s, about 35%. But at the end of April, it was almost 70%, so almost twice the moisture that it had just 3 months earlier. Interestingly, if we go to the other end over here, we look at mountain laurel, we can see that the foliage actually decreases in moisture at least throughout the spring. So it's going to be really interesting to see how this plays together and how these attributes of moisture will feed into this fuels library that we're developing. Another thing that we're working on is field-scale fuel experiments. And so we're actually doing, here we go, we're doing burns both in low fuel loading conditions and in higher fuel loading conditions. And Nick probably talked about these in the last webinar. And we're looking at how a range of fuels impact fire behavior at different scales. So one of the neat new tools that's available is a terrestrial laser scanner or a terrestrial LiDAR unit, and we can use that to create high-resolution digital representations of the forest, and we can subset them. This is our research plot, and this here is our experimental setup that has equipment that measures the aspects of fire behavior. And we can look at how fine-scale variation in fuels is impacting fire behavior. And so if this is a downward view of one of our plots, and we can start to map out things like fuel. So if the blue lines represent sticks on the ground and the green dots represent pine cones, we can actually determine that from the LiDAR, what their distribution is across the plot. And then we can burn these plots and see how at different times of year, different environmental and fuel conditions are impacting fine-scale fire behavior in these experimental plots. We've also got a FLIR camera up on a tower, and I was having some issues with the video last night. Like I said, we're just coming off of a field campaign here, and I was having some trouble getting the software to write the video. But in the picture on the left, there's a tower, and up on top of the tower there's a black thing, that's the camera. And then in the picture on the right, Nick's using a joystick to actually move the camera in real time, while one of our local fire managers is looking at how that fire behavior is varying and how the temperature in the plot is varying during that burn. So after the burn, we can take another set of LiDAR data. We burn the plot. We've watched how the fire progresses across it in relation to fuel. We can come back and scan and look at things like how the fuel changed in depth just across that small plot. So this is our pre-burn picture of the surface of the fuel near a tree. And if we go ahead, we can look at the post-burn image, and we can see if you look right along here, you can see a pretty, see if that goes back. You can get a pretty small, it'll pick up very small changes in the fuel structure on the scale of centimeters. And so that's pretty interesting because we can build digital elevation models and subtract them and get a difference of fuel loading after we do these burns. And so this is a great non-destructive way to go measure both the pre-fire conditions and the fire effect in terms of fuels. So moving forward, that's about all we have for data at this point. We're kind of deep in the process of analyzing what we've got right now and looking forward to collecting more data moving forward. We're looking forward to building this fuels library with different species and different seasonal aspects of those species. And our colleagues are going to be building information about how these things combust leaves and twigs using their laboratory capabilities. So we can look more at how different species regenerate with time, and we can also, we're going to continue these field scale experiments and look at how things like different amounts of shrub in the forest impact flow, and how different mixes of shrubs have a different impact on fuel moisture over time. We can look at how fuel dries and wets under different forest conditions. So if you've burned before, you'll know that shaded areas will dry slower than more open areas. And the more you burn, the more you open up the forest. So as we treat the forest, we're also changing these dynamics through time. And then we're also going to do more experiments where we vary the fuel bed conditions. So different mixes of different species of leaves and different loadings of fuel, and studying how that incorporates into fire behavior on this small field scale. So as you've kind of gotten it beaten into your head, there's going to be more webinars coming up over the next couple months here, and this is just some of the crew picture that was taken after our last experiment last week here at the Experimental Forest. And just about everybody in this picture is going to be giving another talk that relates to this, but on a different subject very soon. So as these progress, we're going to have more and more results, and it'll be pretty interesting to see how everything connects. So that's my plug to stay tuned. But I'd like to open up the floor for any questions now. Maybe you can unmute the phone line, Amanda, or we can actually put them in the box here. That would be great.
Yeah, awesome. Thank you. Yeah, and we have plenty of time for questions. We don't have to go the full hour, but if you got lots of questions, we can certainly take it. So Tim Simmons has a question. He asked, what will the geographical extent of the completed fuels library? I guess what will be the geographical extent of the completed fuels library?
Yeah, so that's a great question, Tim, and we've been kind of tossing that one around a bit. So at this point, I think we're going to focus on some key species that have a broad geographic extent. So probably things like scrub oak, lowbush blueberry, black huckleberry to start. It takes quite a bit of time to measure these things. And so I think for now, this project's going to go on for another couple of years. I think we're going to try to hit some of the ones that have like I said, the broadest geographic extent and that are the most prevalent here in our different types of upland forests that burn a lot. And then we can kind of, depending on how that goes, we can expand down the road. But if nothing else, this will set a good framework that can be added on to with future grants and time.
Great. Yeah, other folks can definitely type questions into the chat box. Actually, building on Tim's question, I had a related question. So in that fuel library, what was the scale at which you took the measurements? Was it, did you measure individual plants? Was it on a plot of a certain size, or did you extrapolate to per acre?
So for the fuels library, the idea right now is to develop basically a library of plants that modelers can incorporate into their simulations. So there's not a lot of data available as to like what a shrub looks like. How much of that shrub is going to be 1 hour fuel and how much is going to be 10-hour fuel, say if you're a scrub oak. And so we're looking at the individual plant scale right now, and then modelers can say, all right, we want to build a fuel bed, and we're going to put, maybe 50 huckleberries in, and we're going to simulate another 18 scrub oaks, and we'll see how that works out. And so they could actually pick and choose different numbers of realistic shrub representations and change the numbers of them, look at them independently, or build their own sort of novel or shrub environments in their simulations.
Okay, cool. So we'll give folks, definitely, if you have questions on anything that Mike presented, please type into the chat box. I have another sort of follow-up question, not just about the fuels library, but looking at the LIDAR pictures, how do you see the LIDAR and the DEM fuel models sort of translating to a bigger scale, for application?
Yeah. So that's a good question. So right now, I'm trying to find the right picture here. So here we go. So that didn't go. So yeah. So right now, this field scale LIDAR is really informing flow on a fine scale, and it's a little bit difficult to say how that's going to scale up to the, I'd say to an operational level. I'm not sure if that's actually the biggest part of the goal right now, as it is to really define how fine scale attributes of forests and weather interact. There isn't really LIDAR data available for everywhere. There's some complicated, I'll just say that there's some complicated things about using LIDAR at an operational scale, or if we're doing operational scale measurements. But we are actually using some new LIDAR units to do plot level fuel measurements, and these are types of units that may very soon become something that fire managers could use to analyze plot level fuel loading and effects in their management. So these tools are starting to get a bit cheaper. They're a bit easier to use, and their images or their data products that they produce are getting better. So I don't know if that exactly answers your question, but at this point, so we will be doing some large-scale experiments next year where LIDAR data will get incorporated. But as far as incorporating that into operational tools, I think we're a little ways off. So one thing that's useful to know is that the scale of the data that go into the existing fire models is like Behave is quite big, and there's just a lot of the physics that connect structure to fire behavior. That's kind of that's a big part of what we're investigating, because there's some knowledge gaps there. So I think it'll take a little bit of time to know exactly how that can best get used across a larger scale. And that's kind of part of the iterative approach of this project is to bounce back and forth between scales and as we learn things, take it to the next level, and then fall back and to a larger, smaller scale as needed to fill in the gaps.
Great. Yeah, we had a couple additional comments that came in kind of building on what you were just saying. Nick Skronsky added, the idea is that we will build a model of something at the finest scale that we can, individual plant. Then we can populate a fuel bed, quote unquote, with those individuals. These would all have some characteristics that can be simplified and scaled up to the larger model domain. And then Tim Simmons chimed in, it sounds a bit like the methods we used prior to the 2005 revision to develop custom fuel models for the variability we find in our fuels in different seasons. Nick actually has another question/comment. He says, a question that we are asking is which things are important to know at the small scale that we need to carry forward to the large scale? We have to find efficiencies and focus on where the variability is important.
Right.
So
yeah. Those are really good comments. And that's I mean, of course, Nick is quite involved in this project, but that's a really good way to put it. That we're still learning about scale, quite a bit about scale, and really what scale is necessary, at what scale things change, and what scale we even need to be measuring things at. And so, yeah, starting sort of at the least common denominator, which is sort of the fuel particle or an individual plant, and then kind of going up from there and revising our understanding is a big part of this approach.
Yeah, so for folks in the webinar or on the line, I'd encourage you to type a question or type your thoughts into the chat box, sort of an answer to Nick's question. You know, which things are important to know at the small scale that we need to carry forward to the large scale? And while folks are maybe typing an answer or another question, Woo-Jung Park has another question. He says, I have a question related to a 3D image from LiDAR. Is this 3D image going to be voxelized image, or will it be a 3D CAD object?
So I guess I'm not exactly sure what the final outcome is going to be. You can kind of produce a range of different data products once you have a LiDAR scan. I think we're going with like a wireframe model at this point. But depending on what different people will use these in different ways, I suppose. But it seems like right now for flow modeling, it seems like a wireframe image might be the best. But I'd be happy to actually hear more about your ideas on that.
So let's see. I don't see other questions in the chat box at the moment. I'm thinking about opening up the phone line
Sure.
to see if you want to continue with any of this, because we might have some people that are like, oh, I don't want to type long words right now. So, okay. So people have not, okay. Megan Tabaski has a comment. She says, this is awesome and exciting work. Looking forward to further results and conversations about scale and mapping with a smiley face. So indeed. Thanks, Megan.
Thanks, Megan.
Yeah, definitely great conversations, and thanks for being part of this. So I'm gonna unmute the phone line in just a minute. So if people wouldn't mind, mute your individual phone line unless you have a comment or question to share. So unmuting now. So now the participant lines are unmuted. If you have a question or a comment or another discussion point you want to bring up with Mike, please speak. Don't be shy. I have a question for folks on the line. So we have a variety of perspectives of folks that are here. And going back to Nick's question about, which is important to know at the small scale that we need to carry forward to the large scale. We have people with kind of ecological goals. We have folks with safety goals. We have folks that work in the WUI scales and structural protection. We have folks that are doing other research. So what do you think might be important to carry from the small scale up to the big scale? Feel free to either type it or say it out loud on the phone line. So
I guess I have one that I can just add, and that would be so there's a big difference in objectives between wildfires and prescribed fires, and some of the tools that are available now are good for large-scale planning purposes for wildfires, but when you're burning a prescribed fire, there's smoke management is a big issue, and perhaps a bigger issue that you're on the hook for. And so, again, how we came back to, I've mentioned flow a bunch of times, but these different balances of fuel loading and moisture, as we saw in the one picture, can really impact the completeness of combustion and the energetic release from that fire, which can really do a lot to control how much smoke is produced and how that gets lofted, and in turn also that can impact the amount of heat that's transferred to the vegetation that's there. And so if you're looking to some of this information I think could become quite useful in learning how to meet multiple objectives, or what points you can meet multiple objectives with a prescribed fire, and what some thresholds might be to getting there.
Yeah, that's helpful. Cool. Anybody else out there have a question or comment you want to chip in, Mike?
Yes, Albert speaking.
Hey, Albert.
From the WPI. Hi, Mike. Nice talk, and I think something you described is the problem of understanding how we transfer, or how actually not only we transfer information that's with the modeling, but how the physics is transferring a small scale events like combustion or like the burning dynamics of the thinner fuels to the large scale, and to looking at the fire front dynamics in general, even at the scale of prescribed fires. And so as it is vegetation which is burning, everything we can do in modeling will need to have a description of those scales. So for us, it's very important to have access at those scales, access to all those scales. Doesn't mean that we need to have access to all those scales at the same time, but basically, when you do a model, by definition, you do a simplified representation of reality. And so, and because it's wildland fires and it's extremely complex, or prescribed burns is the same, you just need to make strong simplifications. Even with the CFD models, we're still making strong simplifications for some of the submodels, or some of the physical mechanisms. So getting the information about the different scales helps us to track the physics, and then to say, even if we're making an assumption and the description of a given experiment, like you showed the small plots, we don't take into account everything that we measured, but we can make the difference between what we measure and then what we model, and say, basically, we're capturing enough of the physics to be able to present the fire behavior and the fire dynamics, and that's very important. So there are two levels, and you touch on the two of them. There is model verification and validation, and then there is also input for the models when you want to run the simulations to make a prediction or to make an assessment once you've trust the model enough to do that. So it's two very different things. So for the first aspect, we really need to get everything and to build trust in the model, and then that will help us to define what are the real inputs that we need for the other types of applications.
Yeah, thanks, Albert. That was good. I like that you hit on the validation and verification of models. And that's one of the nice things about this design here is that we can actually we can actually make a hypothesis even about how the fire is going to burn across the plot once we've populated this model with all the information and the functions of how fire behaves. So that's already underway. That the model's being developed, and this fuels data is really going to feed this existing model that's being developed. But the ability to make a hypothesis then and say, okay, we think the fire, now that we know what we know, we think the fire is going to do this, and we can create that condition and even test it and see if we're measuring the right things or how good our simulator is doing.
Yeah, and I would add that a lot of the aspects that we're simulating are better known or coming from other science. That, for instance, when we're simulating the flow and even the turbulence, we know a lot. What we don't know usually is linked to vegetation. So this is very critical. There will be no progress in the models if we don't progress our representation of vegetation from the models and our understanding on how vegetation interacts with the flow and burns. So that's very critical for us. We cannot progress substantially without that.
So that's pretty interesting as well, Albert, and that kind of brings up a conversation that I had recently with two of the students from Edinburgh. But so in ecology, every plant, every animal, everything, form follows function. And it's something that's been largely overlooked in fire ecology is how the form of plants might actually feed back into fire behavior. So we know that certain things burn more than others. Certain leaves, observation we've seen that, mesic species of leaves, or those that tend to be on wetter sites, typically also don't burn as well when they're dry as maybe something from an oak or heath vegetation type wood. But there's all these structures on plants, especially in our environment here, the pine barrens. So, pitch pine, you've got these serotinous cones. That's a structure that's made for fire. You've got this bark that sheds heat by losing bark during a fire and is insulative. That's a structure that's made for fire. We can look at the moisture content of the pine needles and see that come up with reasons why that actually might be the best time of year for a pine to burn even. And so how it's not a far leap to really think about how these different plant structures that make up the fuel bed actually could have there's a lot of reason why for ecological competition, why there's likely an evolutionary history that makes them burn one way or another for their own benefit or for their neighbors' demise even. And so visiting this whole plant structure and property question is just really interesting.
I want to just interject real quick. Megan had a good side back to your initial slides. She says, related to the caller's comments, in addition to scale, it's about the question you're asking, whether you're looking at smoke, flame length, intensity. For different variables at different scales, you'll want or need different levels of complexity, like the seats inside your airplane from that earlier slide.
Right. Yes. Yeah. So totally like that. So, yeah, really the scale of the question or the scale of the phenomena really has to guide really the scale of measurement that we're looking at.
I see we're about 9 minutes until 1 o'clock Eastern time. I just want to see if there are other folks out there that have questions. We'll give folks a few seconds to pipe in.
I could just add to Megan's comment there that in a wildfire context, one of the things that we're really interested in from a a fire suppression standpoint is whether we're in the worst case scenario or not, whether the conditions are lining up to basically be in that that red danger zone or not. and with you know, I guess I mentioned prescribed burning a lot, but so that's kind of like one scale of operation, you know, safety. But then for other types of burning, we're kind of working in a more probably a less volatile environment, and where we're kind of really thinking a lot more about these nuanced conditions to get very specific fire behavior. And so the scale of that, the scale of objectives is much finer. And so that's just a difference there in sort of two different needs in fire management, I guess.
Cool. Let's see. We have folks another moment to type any questions in. If not, we might be able to wrap up a little bit early.
Sure, sounds good.
Ken Clark says, nice talk, Mike. Thanks. Thanks, Ken, from Ken, Carlos, and Zach. So, yeah, great. Thanks for joining us.
Thanks for
Sounds
tuning
like
in,
folks are getting ready to wind down. I'll just mention our next webinar 2 weeks from now. We'll have Dr. Bob Cremens from the Rochester Institute of Technology. In the same project, he'll be talking about progress towards precision measurement of gradient and convective flows in wildland fires, the history and the current state of the art. So that's going to be more fun and more cool fire science gadgets for 2 weeks from today, and a lot, obviously, of the science behind that. So I think we'll end now. Thanks, everybody, so much for joining, and please feel free to contact us if you have questions. And thanks again to Mike. Thank you.
Thanks, everybody, for tuning in.